Okay, welcome back for another lecture on Chapter 13, Alcohols, Phenols, Thiols, and Ethers. Hopefully you were just wowed by alcohols, phenols, and thiols and couldn't wait to get here into the next portion of Chapter 13. All right, and here it is, the last of those four topics that Chapter 13 contains, Chapter 13.2 ethers. So ethers are a little different. The alcohols, phenols, and thiols, at least the alcohols and phenols were OH groups, hydroxyl groups. In the case of alcohols, they were just bonded to a regular chain carbon. In phenols, they were bonded directly to the carbon in an aromatic ring. Finally, thiols, just like the alcohols, are bonded to typically non-ring carbons, but their claim to fame was that they were SH groups as opposed to OH groups. Finally, here we're ready to discuss ethers. I can't wait. I bet you can't either. Okay, so an ether is an oxygen-containing hydrocarbon, just like an alcohol or a phenol, but in this case, the ether consists of an oxygen atom that is connected by single bonds to two carbon groups, alkyl or aromatic, and again, we would call this oxygen a bridging oxygen because unlike alcohols or phenols, where the oxygen was essentially terminal. It had an H on it, but it didn't extend beyond that. Here, ethers can be in the middle of very large compounds because of the ability to extend on either side with those carbon groups. We're going to hit that idea of simple naming according to IUPAC versus non-IUPAC. Simple ethers, which are the majority of the type we'll encounter, are named by listing the alkyl names in alphabetical order, followed by ether. We also have an additional way to name, as you see down below. So dimethyl ether there is the common name, or methoxymethane is IUPAC. We see in the right-hand case we have an ethyl and methyl group, so that's ethyl methyl ether, again named alphabetically, not in order of carbon length. That's why the ethyl group is first, because it is alphabetically first, even though it's longer than a methyl group. And of course, that's not the case with IUPAC. With IUPAC, this would be methoxyethane. So we would be looking for the longest chain to be named second, and the first chain to be named first. Now, even when I said the word ether, you probably thought of ether, the anesthetic, and early anesthetics were typically ethers, and in particular diethyl ether was a very, very common one. If you watch any old Bugs Bunny cartoons or any of that where there's the bottle of ether, it's usually diethyl ether that they mean, and diethyl ether is a very effective anesthetic. It works by inhibiting pain signals to the brain. It caused nausea, which is unpleasant. They were flammable, which is potentially dangerous, and so they've largely been replaced by other anesthetics, but they were important in early medicine because they were tried and true, and they were about all that was at the ready disposal of most physicians or hospitals. You see some other ethers down below, and those are some just a little more elaborate examples of anesthetics compared with good old diethyl ether. Now, cyclic ethers are an important subclass of ethers that contain the oxygen atom within a carbon-containing ring. It's known, therefore, as a heterocyclic compound. When we talked about the cycloalkanes or cycloalkenes or cycloalkynes, we had, again, everything in the ring being a carbon atom. Now we have an example of a ring that has a member of the ring that's not necessarily a carbon atom. In this case, for cyclic ethers anyway, it's an oxygen atom, and that's important. And that's, again, heterocyclic compounds are important, biologically speaking, especially, and so that's why we take a little time here when we're introducing ethers to talk about these 5-membered or 6-membered rings, and we'll see when we get to carbohydrates. So furan is a 5-membered cyclic ether, so 4 carbons and an oxygen. We'll talk about furanoses when we get into carbohydrates. Tetrahydrofuran is a very common organic solvent, THF as it's commonly abbreviated. Pyran is now a 6-membered ring with one of the positions being an oxygen, a bridging ether oxygen. And we'll talk about the pyranoses when we get into carbohydrates. So it is relevant, it does matter And then finally, 1,4-dioxane is a compound that's suspected or maybe known by now of causing cancers and things like that. And so that's something you might have seen or heard about, maybe not by the 1,4 name, but dioxane. It's been something that's been discussed for some time in the common literature. Now, not to be confused with dioxane, which is, again, I think it's still just a suspect cancer agent. It's known to cause cancer in rats that are exposed to it over their entire life, but I don't know about humans. I don't think the EPA or any other group has officially considered it a known carcinogen, but it's certainly a cancer suspect agent. The dioxins are a six-membered ring with 2 oxygen atoms and 2 double bonds, and so they're a group of ethers that are highly reactive, and these are indeed often carcinogenic to humans. And they're formed during forest fires and as industrial byproducts. Unfortunately, a lot of firefighters happen to develop different cancers or other illnesses from their line of work and die, unfortunately, younger than the average individual. So it's possibly these dioxins as well as other substances that they don't even know they're exposed to that contribute to those higher incidences of cancer. But you know, that goes along with being a hero, I suppose, is risking one's life in the short term and in the long term to do the right thing. Okay, now a few slides back, we saw some common names and IUPAC names for ethers, and we talked a little bit about the common naming system. We look at the two sides of that oxygen, and we name those groups as we would for alkanes, and then we just put them in alphabetical order with ether at the end. When we use the IUPAC system, what we are considering now is the shorter alkyl group is named together with the oxygen as an alkoxy group attached to the longer alkane. So if we look at this particular example here, we have a methyl group on one side and a propyl group on the other. The methyl group is just 1 carbon, the propyl group is 3 carbons, so we have a methoxypropane. In this case, we would number this longer alkane to give 1-methoxypropane. Okay, so there it is. That's our IUPAC name. It's a little more difficult than the common name. So common names are particularly prevalent for ethers because the common naming scheme is just so darn simple. So it's probably the one time you and I would both prefer the common name because the IUPAC name is a little unwieldy, but we still need to know it. But it's a case where you may actually see me ask about the common name as much or more than the IUPAC name. It doesn't mean the IUPAC name is not important. So here's our guide to naming ethers using IUPAC conventions. So we write the alkane name of the longer carbon chain. We name the oxygen in the smaller alkyl group as an alkoxy group. And then we number the longer carbon chain from the end near the alkoxy group and give its location. That's why we ended up with a 1-methoxypropane in our example on the last slide. So here's our generic guide to naming. Since we already did one together on the previous slide, let's go ahead and see how you do on this next learning check. All right, here it is. In this learning check, you're asked to give the IUPAC name for the following. You might also want to give the common name since they're so much fun. But go ahead and at least for the IUPAC name and hopefully also for the common name, write those down and pause the video while you do that work. Start us back up when you're ready to check your work. Good luck. Okay, and here it is. So following our steps, first in step 1, we write the alkane name of the longer carbon chain. So on the left-hand side, we have just a methyl group. And then if we look to the right of the oxygen, we have 1, 2, 3, 4, 5 carbons. So that's a pentane. So that's the alkane name of the longer carbon chain. Step 2, name the oxygen in smaller alkyl group as a substituent called an alkoxy group. So there we have a methoxy group because of just having that methyl 1 carbon on the left-hand side. Finally, here in step 3, we number the longer carbon chain from the end near the alkoxy group and give its location. So here we have carbon 1 directly connected to the oxygen, and then 2, 3, 4, 5. So we have 1-methoxypentane. if you wanted to name this thing according to the common naming scheme, this would be a methyl pentyl ether. Okay, so this is one time you're likely to see the common name asked by me almost as much, if not more frequently, than the IUPAC name. But to do your due diligence, you need to be able to name in either scheme. We're having way too much fun to stop now. So here's another learning check, and in this learning check we've got some skeletal structures, and you're asked to name each of the following. So we have those two skeletal structures. Go ahead, stop the video here while you name these things, and start it back up when you're ready to check your work. Good luck. All right, and so for A, notice here we have on the left-hand side the larger alkyl group, and the smaller group, the methyl group, now is on the right-hand side as opposed to our prior learning check. So we have the cyclopentane is the name of the longer carbon group. The methyl group gets named as a methoxy group, and because there's really no position on the ring, unless we had more than one species, we don't have to worry about the one part. So this is just methoxy cyclopentane, or if you like your common nomenclature here, it's a cyclopentyl methyl ether, right? The cyclo actually goes into the alphabetical name, so that's why it comes first. If it was pentyl, just plain old straight chain pentyl, we'd name it as a methyl pentyl ether, but this time, because it's a cyclopentyl group, it's cyclopentyl methyl ether. All right, so that was probably the easier and the more fun one. B, you really just had to sort of remember from that slide that this is the 1,4-dioxane. And again, this is probably one of the few that's actually stable of the dioxanes. So the other ones are just temporary, short-term reagents that are reactants along a greater pathway. And this is the one that does cause nasal and stomach cancers in rats who are exposed. So probably not great for us, although I don't know if it's officially been listed as a known carcinogen in humans. And before we leave our second lecture here in Chapter 13 on ethers, we have one last learning check, and this one asks you to draw the condensed structural formula of each of the following compounds. And again, of course, hopefully you're also practicing skeletal structures, because those are helpful, and you'll certainly, if for no other reason, you'll look more like a chemist if you start drawing those skeletal structures. So hopefully you're working on those as well, but at least the condensed structural formula for each of these three. Pause the video here while you complete that work and start us back up to check your work. Good luck. Okay, so for number one, it's using the IUPAC nomenclature, so it's a 1-ethoxypropane. So we have an ethyl group on one side of the oxygen, a propyl group on the other, and because it's a 1-ethoxypropane, we know that we're connected to that terminal propane carbon. If it were 2-ethoxypropane, we could be on that middle carbon, and we could have sort of that isopropyl group, if you know the common name, or 2-propyl group by IUPAC. For B, we've got the common name, and things probably went very well for you there, ethyl methyl ether. Doesn't matter if you have the ethyl group on the left and the methyl group on the right, or vice versa, because of course we can flip these things around in 3 dimensions. Finally, C, 2-methoxybutane. Here's finally one that's not a 1 something, right? So that's what I was getting at with the, if it were a 2-ethoxypropane up in A, we would have been sort of in the middle there of the propyl group here. Because we're a 2-methoxybutane, you're seeing a little bit of that. So you have the oxygen, the methyl group, and then carbon 2 of the butane is where that bridging happens. So not everything's a 1, and not everything's a methoxy either, although I think we've overused that example, but there you have it. So hopefully this little subsection on ethers has gone well. It's just the one type of compound to deal with, as opposed to the alcohols, phenols, and thiols we did in the last lecture. So hopefully by isolating it just to the ethers, things have gone well, and you've been able to get a lot of good understanding. If that's not the case, if you're struggling with ethers, please don't hesitate to get in touch. Okay. Otherwise, hopefully things are going well and you're ready for the next lecture, and I'll see you in lecture 3 on chapter 13.